So I'm starting with just this idea of having you visualize what these two graphs would look like, because getting these ideas down is going to help us a little bit later when we get into one of the details. The line y equals 5. Now, generally speaking, everyone ends up saying, oh, that's easy, it's a straight line. Okay, first of all lines are straight. Okay, so the straight aspect of that doesn't really help us any. But usually it ends up coming down to one of two things that's meant by that. Either the person is meaning that we have a horizontal line at 5, or the person is meaning we have a vertical line at 5. The question is, which is it? And partly it's a little counterintuitive if you're thinking of axes, which is why we talk about this. Think about where is a single point where y equals 5. Well, if I were looking for a point where y is 5, almost everybody would start by thinking of this point. That's where y equals 5. And then that can already tell you, but then I might say, okay, well, what's another point where y is 5? And sometimes that gives people trouble, but remember, if y is 5, x can be anything. X could be 1 and y is 5. X could be 2 and y would be 5. Notice every single point on that horizontal line is y equals 5. Which means that x equals the negative 3 is going to be the vertical line. So y equals 5 is horizontal, x equals negative 3 is vertical. It can be a little counterintuitive just because we think of the y-axis as going up and down, but of course the line y equals 5 doesn't work the same way. Because it's not the axis, it's just a description of all the points. Alright, so today we're going to be getting into graphing stuff like this. We're going to be getting into graphing exponential functions. Above your first graphing grid, please write this equation down. The y equals 2 to the power of x. Now, since this is the first time we're making a graph that looks like this, I'm just really quick going to go ahead and just make a table of values as a way to track what it's going to look like. So we're going with x and y values. And just for this one, I want to know in particular certain values, so I'm just going to go ahead and start filling in my x's. I'm going to start negative 3 and just go up from there. So these are the ones we're actually going to work with. Now, we can go ahead and do all of these off the top of our head, but I know the negatives, they're going to provide a little hitch in our giddy up here, so I want to start with the easy ones. Let's start with just 1. What's 2 to the power of 1? 2, yeah, because it just means a single 2. So that gives me the point 1, 2. I can go ahead and plot that on my graph as well as I go here. Then I go to x being 2. So if x is 2, what is y? That would be 2 to the power of 2, which, yes, is 4. And so again, I can plot that point at 2, 4. Notice these are actually coordinates. It's not from the last point go over 2 up 4. It's actually the coordinates 2, 4, because we're making a table here. All right, next up, if x is 3, that means we're doing 2 to the power of 3, which is 8, because it's 2 times 2 times 2. And so then I can plot the point 3, 8. All right, now we can go ahead and fill in the rest of these, but they do require you remembering some of your exponent rules. For instance, the next one up, x being 0. Anything to the power of 0 equals what?
0.
1. That one's an easy one to forget, but it is 1. And you'll actually kind of be able to see by the time we finished our graph why it has to be so, otherwise our graph would make a weird little jump in the middle. Okay, what about negative 1? Well, now we're really going back to remembering the negative exponent. So I have 2 to the power of negative 1. Remember that a negative exponent flips it in the fraction? So that's going to be the same as 1 over 2 to the 1. Well, so that would be 1 over 2. So it's 1/2. So that gives me the coordinates negative 1, 1/2. So I can go ahead and plot that. Yes, I know the 1/2 is not on a grid line. That's okay. We can still just get as close as we possibly can. Just be as accurate as you can as you do it. So then for the negative 2, again, think about what the negative exponents mean. 2 to the negative 2 would mean that we're doing 1 over 2 to the 2. And so that would be 1 over 4. So now again, I got a point I can plot. -2, 1/4. Okay, so -3. What would 2 to the -3 be? Yep, it's 1 over 2 cubed, so it's 1 over 8. And then we're definitely estimating where that's located when we plot that point, right? Now notice the pattern of what else going on in this graph. Every time I go to the right 1, it goes from 1 to 2 to 4 to 8, I'm multiplying by another 2 in there. So in other words, as I go to the right, I'm multiplying my last value by 2 as I go to the right. Well, if I'm multiplying by 2 as I go to the right, what am I doing as I go to the left? Yeah, we're dividing by 2 as we go to the left. And the nice thing about that is that if you know that pattern, you don't have to make the table every time. You can just plot that first point, which generally speaking is going to be right there at 1, and then you can double them to the right and cut them in half to the left, which also lets us fill in a bunch of these other little points on the left side here, because we can just keep cutting that in half, but all of a sudden they start getting really, really small, right, as we go to the left. Question: as we go to the left, and we're getting really close to the x-axis over here, do I ever actually hit the x-axis?
No.
Well, do I ever actually hit 0? No. Because I'm always taking some positive number here and I'm cutting it in half. Well, the only way you get 0 by cutting it in half is if you start with 0 and cut it in half. And of course, we never reach 0 in the first place. So these numbers are just getting super close to 0, so close that when we plot the points on the graph that they're basically on the axis. But we do need to remember that they never actually hit 0. They just get super close to it. Now, this graph that we just sketched in there, this is an exponential parent function. So as we describe these, x squared, that was a quadratic. 2 to the x, that's exponential. Exponential refers to any equation where the variable is in the exponent. So it's something to the power of x. Now, little subtlety, little detail. You notice I said here that it is an exponential parent function. There's actually any single number to the power of x will be a parent function. So 2 to the x is a parent function, 3 to the x is a parent function, 0.95 to the x is a parent function. So anything where you just have the number to the x is considered parent. Now, one of the things that's unique about the exponential equations is that they include this set of points here where the further out I go, the closer I get to 0. Well, a lot of graphs actually have this characteristic where the graph is approaching something but never actually hitting it. That line that it's approaching has a special name. That is called the asymptote of the graph. And so since we're now going to be working with graphs that involve an asymptote, we should probably put that definition down to our notes. So go ahead and add this into your notes now. All right, and now that we have the definition of asymptote, let's go and actually see how we would describe it when it comes to that graph that we just looked at, our 2 to the x. So here, we would actually say that the asymptote is at y equals 0. Because remember, I started with saying, okay, what's the graph of y equals or x equals look like? Which one's horizontal, which one's vertical? That's so we can keep it straight about the asymptotes being horizontal, meaning that we write it as y equals that number. Now you notice I've drawn it in on the graph as a dotted line. That's actually fairly standard. When you have an asymptote in a graph, you represent it graphically by drawing a dotted line. It must be dotted because we're showing that this is an important aspect of the graph, but these are not actually points on the graph. If it was solid, that would mean that these are all points on the graph as well. So different kind of meaning there. So for y equals 2 to the x, our asymptote's at y equals 0. Now we can start messing around with our graph a little bit. So we're going to be graphing this. Just y equals 2 to the power of x minus 1. Go ahead and write this equation down for your next graph. All right, so the first question is, what's the parent function? Well, the parent function, remember, is our basic equation, the one that has all the extra stuff stripped away from it. In this case, the minus 1 is a transformation. If I take out that transformation, notice what I'm left with. I'm left with just y equals 2 to the x. So that's our parent function. I always like to think about what the parent function is because it tells me that this graph will look and behave exactly the same as what the parent function does. And so I already know what to expect from the graph. I just also need to know how it's been transformed. So that's what the next question is about. So what does a minus 1 hanging on the end of our equation do?
Would that be where the...
Yep, that number hanging on the end, that shifts it because it's addition or subtraction, and the one on the end shifts it down. And so for the transformations, we would say shift down 1. So notice then what we're really saying then is I'm going to take my same graph that I made, but just I'm going to move it down 1. And when I move it down 1 then, that moves the asymptote as well. And so my asymptote now is no longer going to be at 0. My asymptote is going to be at y equals negative 1. Now, for the domain and range parts that you have on your paper there to fill in, we'll save those here for a moment. We're going to make the graph first, then we'll fill in the domain and range. All right, so for making our graph, step 1 of making an exponential graph is to draw in the asymptote as a dotted line. And as you're doing this, it might be valuable for you to write down the steps that I'm telling you. Actually put those words in, but at the very least, draw it on the graph. All right, and then I can start looking at plotting points. Well, the first point is typically the same thing, because anything to the power of 0 is what again? 1. Now, when I say 1, though, because remember I moved this whole thing down, I'm specifically meaning up 1 from the asymptote, because the asymptote is kind of acting like our new 0. It's our new starting point. So my first point starts up 1 from the asymptote. Now, later on we'll get some stretches which will change even that, but for now we know that anything to the power of 0 is 1, so we start up 1. Now, this was 2 to the x, right? As we went to the right, what were we doing to our points again? Yep, we're multiplying by 2. Specifically, we're multiplying the height by 2, remember. And so if I'm actually going to then start plotting points, I just went up 1 from the asymptote. So next I would go up 2 from the asymptote. And then I would go up 4 from the asymptote. Then I would go up 8. I'm always doubling whatever that last height was. So I'm doubling the height as I go to the right. And then if we're doubling it as we headed it to the right, what were we doing again as we head to the left? Yep, we're cutting them in half. We're dividing the height by 2. So our height of 1 becomes a height of a half and then a quarter. They get really small really fast. But we can go ahead and plot the ones that we can be decently accurate about. Once it's below 0.1, it's pretty hard to be very accurate with it. So we know that basically at that point it's going to be like right on the asymptote, visually speaking. And then once you plotted all those points, go ahead and draw your curve that goes through them, and then you've finished out the graph. And now that we have the complete graph, now we can go ahead and talk domain and range. Because now we can see it. So domain, remember domain is talking about our possible x values. So as I take a look at my x values, as I'm going to the left, is there ever a point where our graph stops going to the left? No. Kind of that tail of the graph keeps going to the left. And we pretty much know it's going to be almost right on the asymptote there. So we know about where it is, but it's going to keep going to the left. What about as we go to the right? It's certainly going up quickly, but is it still going to the right? Yes. Does it ever stop going to the right? No. I mean, they're way up there, but it is still going to the right. So our domain then, it's all real numbers. And because there is such continuity between these graphs, because this domain is all real numbers, I can tell you that every exponential graph will have a domain of all real numbers. Because all of them go forever left and forever right. The range, however, is not all real numbers. And so knowing that already, I already know that my range is going to have to deal with y. So the y's are all going above the asymptote, right? That's what we can see happening here. Now where's that asymptote at? -1. And so the -1 is the number that's in the range. That will be true every single time. This number right here is the asymptote. And you notice our asymptote is y equals -1. Well, our range is the same thing, just it's not equal. It's y is greater than -1. But notice I did not say greater than or equal to. I didn't put the line underneath it. Why? Well, remember, it's getting really close to the asymptote, but it never actually hits it. It can never actually hit the asymptote. That's the definition even of the asymptote, is it approaches it, but it never actually touches that line. So it can get as close to -1 as you could possibly imagine, and even closer. But it will never actually reach -1. And so that's why for the first time you have a range where it's greater than, not equal. So now we're going to go ahead and tackle this graph, y equals 3 to the x. So we're going to be seeing what the 3 does instead of the 2. First of all, we're going to go ahead and list out this information. What's the parent function? Well, the parent function, remember, is what's left if we strip away the transformations. Changing the 2 into a 3 is not a transformation. It actually is just changing what the parent function is. So our parent function actually is what we're starting with here. It's y equals 3 to the x. And if our equation is the parent function, that means there's no transformations. And if there's no transformations, where's our asymptote? Yep, still at 0. And so then our asymptote is y equals 0, and so then I can even start making the graph. Because when I go and start making the graph, the exponential, they always have an asymptote, so I can go ahead and draw that in as a dotted line at 0. And anything to the power of 0 is 1. So I can go ahead and plot that point right away as well. You notice, that's going to be true no matter what is to the power of x. I could have given you y equals 1/2 to the x. And it would still be looking the exact same here at the start. Because our asymptote isn't affected by that, and that first point at 1 isn't affected by it, because anything to the 0 is 1. But the rest, now that does change a bit. So, the 3 to the x, basically what the 3 is going to mean is that we're going to be tripling the height of each point. Because 3 to the power of 1 is 3. 3 to the power of 2 means multiplied by another 3. So 3 to the 2 is 9. So 3 to the x means as we head to the right, you go times 3 instead of times 2. So then, as we go to the left, what do you suppose we're going to be doing? Yep, we're going to be dividing our heights by 3 there. And so I can go ahead and put in some points on the left-hand side as well. But notice, I very quickly end up in some very tiny points. It's hard to be accurate in saying we're going to go to 1/3 of that, which is actually at 1/9. And so once I know that part, I can go ahead and start sketching in my graph. All right, so now having made our graph, what is our domain going to be? All real numbers. And it's exponential. They're all going to be all real numbers. What about our range? Well, the range is not all real numbers, so we know it's got a y in there. The number with the y is always the asymptote, so you know it's a 0. And then it's just a matter of, are my points above it or below it? And since they're above the asymptote, its y is greater than 0. Next graph, go ahead and write down this equation. All right, so first up, we need to know what our parent function is. Well, again, basically you think of it as stripping away the transformations. So if I strip away the transformations, which looks like here, that's going to be like the negative that's out front. That actually, the negative is not to the power of x. When we see negative 2 to the power of x, really what it's saying is it's saying like negative 2 to the x like that. Because the negative out front is like saying negative 1 times 2 to the x. And we do the exponent before the multiplication. Sometimes that can throw people off. If I wanted it to be negative 2 to the power of x, I'd have to put parentheses around the negative 2. And then that makes things all sorts of different. So we aren't going to have to worry about that happening. So the negative is a transformation, and the plus 8 is also a transformation. What's left is our parent function. And so our parent function then must just be the y equals 2 to the x. But then that negative and the 8 are the transformations. Well, what does a negative out front of our equation do to our graph? Flips it, yep. Technically speaking, we say it reflects it across the x-axis. But yes, it flips it upside down. And the plus 8 is hanging on the end, so that's going to move up 8. So there's what we put down for our transformations. Now, in just the parent function, my asymptote's at 0. Am I moving my asymptote here? Yes, we are. Specifically, it's going up 8. So our new asymptote is here at y equals 8. And now that I know that the asymptote is at y equals 8, the very first thing I want to do is go ahead and start making the graph. Draw the asymptote in. And then once I draw the asymptote in, I can start plotting points. But all of a sudden with this one, something's a little different. Because I'm not going to put my first point one above the asymptote. But that's because of this reflection, yes. That reflection, it's flipping it upside down. So that's telling me to put my first point one below the asymptote instead. So there's our first point. And I'll tell you, once you know that, once you have your asymptote drawn in that one point, all you need to know is that it's 2 to the x. Because remember that 2 to the x tells me that it's going to double as I go to the right. So it's going to go, it started by going down 1, so then it's going to go down 2, and then it's going to go down 4, and so on. And I know that it's going to be dividing it by 2 as I go to the left. All right, and then finally for domain or range, we know already that our domain should be all real numbers because, hey, it's exponential. They're always all real numbers because it goes forever left and forever right. The range, though, the range is not all real numbers. It's always limited by the asymptote. So notice I already know it's going to be y and 8. The only question is, are my y values greater than 8 or are my y values less than 8? They're below it, so it's less, yes.